Okay, let's talk about solving ODEs. So we're going to talk about everything that you need to know for solving first order ordinary differential equations. We're going to start off with the first thing, which is separation of variables. So if you can have an ODE that can be written in this specific form, like so. So what this means is basically have a function of y on one side and a function of x on the other side. You can basically separate and put dx on the other side. So you can basically have this specific form, f of x on one side, d of x on one side, and then you can integrate both sides and basically you'll be done. So you can integrate the function with y with respect to y and integrate the function with x with respect to x, and you'd have obtained your answer. So this is what we call separation of variables. You're trying to separate the two functions that you have, a function containing y and a function containing f of x. So I'm going to give you examples to just make sure that you understand this. So the first example that I'm going to give you is basically if I were to ask you to solve this specific ODE. So bear in mind, solving an ODE is just finding a solution, right? Which is values of y. Y is equals to what? It's basically an expression. So I should mention this. Solving an ODE is basically finding an expression without a derivative term. So that's basically what we call solving ODEs. Okay, so if you have something like this is straightforward. You have to separate. So make sure that you have a function of y on one side and x on the other side. So 1 over y, that's my function with y. dy over dx is equal to x. So you can proceed to basically have 1 over y dy be equal to x dx. You integrate both sides. The integral of 1 over y is ln y. The integral of x, that's x squared over 2 plus c. So you can introduce exponents on both sides. So e to the power of ln y is equal to e to the power of x squared over 2 plus c. So e to the power of ln y is basically y. This is e to the power of c multiplied by e to the power of x squared over 2, because if you add things, it's the same as multiplying two exponents together. And you know that e to the power of c is basically a constant, right? It's e to the power of a constant, so it can be a constant. You can call that a. So y will be equal to e to the power of x squared over 2. So you've basically found an expression for y, right? Sometimes it's very complicated and you don't necessarily have to find the expression for y explicitly, but the whole point of separation of variables is to basically separate your variables and try to find an expression for y. So it doesn't matter how complicated it is, right? I can give you an equation that basically says dy dx maybe y squared is equals to, I don't know, y cubed x or something like that. What you just need to do is separate and make sure that y is on one side. The whole goal is basically to separate and put functions containing y on one side and function containing x on the other side. So this is one of the most straightforward ways in which you can be able to solve ODEs. The next way that you can be able to solve ODEs is basically using a very popular fact that I'm going to talk about, and that will build up and help us understand what an integrating factor is. So we can basically have what we call an exact differential equation. Okay, so this is like a special case that when you see it, you know that this is what you're looking for, and you can basically do very cool things with this. Okay, so this is basically a special scenario, right? It's one of those things where if you see it, you can tell that this is special. So this is a special case where actually one side can be expressed as an exact differential. So this basically uses the product rule. Now you might be wondering, what is an exact differential? So we're going to get to that in a second. And basically it'll be so much easier for you to understand. So just when you see an expression, you can basically tell that this is an exact differential. So if I were to give you a function and basically give you something like this, right? Can you differentiate this? So something like this, right? If I were to ask you to differentiate this, you can easily see that, oh, okay, this is dp over dx. So first you differentiate this, okay, and then y comes as it is, plus then you differentiate y, so p of x comes as it is, then you differentiate y. Okay, so this is basically what we call an exact differential. So this thing over here. Okay, so an exact differential is basically something of this nature. Okay, so there's a complicated explanation as to what is an exact differential, the other various forms of an exact differential. But for the sake of this video, we're just gonna take it as it is. If you look at this, if I were to give you this function, so basically, if I were to give you a question that looks like this, so you have some function p of x, you have dy over dx plus dp over dx times y is equal to some function q. Okay, so if you were to see this in a specific question, right, and I were to tell you that this is equal to some function q of x, right, you can do very, very cool things, right? First of all, you can realize that, wait, this came from the derivative of a product, okay? So this came from d over dx of p of x, y. It's very easy to see that if you are seeing something multiplied, but then it's the derivative, and you're seeing something over here, but then it's also the derivative, that it was the derivative of the product. So this is very easy to realize. If you're seeing this, it's very easy to realize that this is a solution or a certain concept that might exist. So this is going to be equal to q of x. Okay, so if you do this, you can do very, very cool things. You can basically multiply by dx on both sides. So you can have this p of x, then you can multiply by dx, and you can have q of x, then you can multiply by dx. Okay, now the next thing that you can do is take integral on both sides. So for p of x dx is equal to the integral of q of x dx. And the integral of a derivative is basically doing nothing. So if I were to ask you to differentiate 2x, for example, then I'll ask you to integrate it again. If you differentiate 2x, you're going to get 2, but if you integrate it, you're going to go back to the same function. So integrating something that you've differentiated doesn't really do anything. So you'll be left with p, sorry, I forgot a y here. So you'll be left with p of x, y being equal to the integral of q of x dx. Now you can easily see that I can be able to then find the value of y. Okay, so this is just a way in which you can solve an ODE. If you realize, if you see that your ODE is in this form right over here, right? If you see your ODE in this form, you can basically make this next logical step and then integrate on both sides, and then you're able to utilize this fact and obtain the value of y. So we first start off by learning separation of variables. You can see that this is easily separable. You can put y on one side, you can put x on the other side, but sometimes it's not possible to do that. And the example that we're going to do utilizes this fact of product rule or differentiating products. So that's what we're going to do. So if I were to give you this example and I say, can you solve this ODE? So cos x dy over dx minus sine x of y is equal to x, right? If I were to give you this example, we can easily see that, wait a minute. I have dy over dx, okay? And I have y on this side. Okay. The derivative of cos x is actually negative sine x. Okay. So this is product rule that has been applied to get this specific answer, right? So do you see that you can see it? Even if, let's say, sine x was on this side, right? You could tell that, wait, I can't separate this. I can't let y go on one side and sine x on the other side. It's going to be nearly impossible to do that. But I can see that this is the product rule that was utilized. So what you can basically do is basically say, oh, okay, so d over dx of cos x multiplied by y should be equal to x. So the derivative of cos x is going to give you negative sine x multiplied by y, the derivative of y, dy dx multiplied by the same function cos x. So you can see that this is basically true just by looking at this. So a lot of ODEs solving it in this equation is basically using your own head, right? So it's something that you just see, and with more practice, if you do a lot of exact differential questions, you can easily tell that you need to apply this specific law. So again, you can basically integrate and multiply by dx on both sides. So cos xy multiplied by dx is equal to the integral of x multiplied by dx. So remember, the integral of a derivative is basically the same thing unchanged. So the integral of x, that's x squared over 2 plus c. So you can easily see that, oh, now I have the value of y. So y is basically x squared over 2 cos x plus c over cos x. So you can basically obtain this specific particular equation for the value of y. Okay. So this is what I call, solving an exact differential equation, an equation where the left-hand side can be expressed in this form, right? So that's an exact differential equation where the left-hand side can be expressed in this form, and it's very easy for you to see that, wait, I can just apply the product rule and realize that this is the product of two specific functions, cos y and y. So you just notice that, and you're able to arrive at the solution. But not all functions are going to be this easy. Some functions are not actually exact differentials, okay? An easy example that you can notice is if I were to give you an equation like this, dy over dx plus y tan x is equal to sec x. If you look at this, you can be like, I'm seeing y over here. I'm seeing dy dx. Okay, so this looks like we're going to apply the same product rule, but you realize that this is tan x. So if you differentiate y, you do get dy, but if you differentiate tan x, you don't get 1. So you can't really write any expression that you would know in this specific form. You can't write it, right? So this specific form does not exist because p of y cannot be found in this specific equation. So this is where we need to introduce what is known as an integrating factor.